Modern electronics manufacturing operates at a blistering high speed, with automated surface mount machines placing thousands of components every minute. But downstream, this velocity hits a wall. On the factory floor, human operators are stationed at testing benches to manually inspect boards and log instrument readings. The core bottleneck is that structural in-process testing and final functional testing are completely separate stages. Because these stages are siloed, a dedicated worker spends an entire shift manually transcribing multimeter readings onto paper check sheets. This manual transcription creates errors and introduces a multi-hour delay before data can be consolidated into a useful report. Achieving zero-touch reporting requires the complete elimination of manual data entry by unifying these stages through automation. This transition relies on building an asynchronous data intelligence layer directly at the edge, rather than focusing on physical machine control. The hardware required for this architecture is a standard Raspberry Pi. This device acts as the central computing node for a test bench, replacing the need for a heavy industrial PC. The system operates by fusing real-time visual defect detection with serial instrument telemetry. Combining these data streams allows the system to generate a predictive risk score for every board. The model calculates the probability of a board failing its end-of-line test, returning the final result in under 3 seconds. The ingestion layer starts with the testing instruments already present on the factory floor, such as digital multimeters. There is a common industry assumption that these legacy instruments cannot be automated. In reality, modern instruments from manufacturers like Fluke or Hioki include built-in USB or RS-232 output ports that frequently go unused. Connecting these ports to the Raspberry Pi bridges the gap. SerialReader.Pi captures raw voltage and resistance numbers. Simultaneously, a webcam captures the board, feeding the image to Camera.Pi. By tapping directly into existing ports and using triggered image capture, the system mathematically bypasses the human transcription phase. Next, the system analyzes the captured visual data to identify microscopic structural failures, such as this localized burn defect. The YOLO V8 machine learning model, deployed via Vision.Pi, automatically overlays bounding boxes and confidence scores over detected anomalies. The model is trained to identify specific defect classes, including mouse bites, missing holes, and open circuits. Accuracy is maintained by using established datasets like DeepPCB and FPCB for model training. Visual inspection happens entirely locally on the edge node, returning precise results in milliseconds without ever requiring cloud computation. The vision layer outputs a strictly formatted array containing the specific defect types and their mathematical confidence scores. This process converts ambiguous physical geometry into queryable quantitative data. This leads to a central architectural challenge: how to combine visual defect data with electrical voltage data. The Predictor.Py module uses the XGBoost algorithm to act as the core engine for this fusion. Stream A provides the geometric anomalies and severity metrics detected by the vision layer. Stream B provides real-time resistance and voltage numbers pulled directly from the instruments. XGBoost cross-references these streams to detect correlations, such as a minor visual scratch that coincides with a slight drop in resistance. This results in a final risk score between 0.0 and 1.0, indicating the likelihood of an end-of-line failure. Predictive fusion allows engineers to catch functional failures during the initial in-process stage, preventing high rework costs later. Once the risk score is generated, the system must distribute it to the correct personnel immediately. The FastAPI backend asynchronously routes this data to 3 distinct locations. First, the data is saved to a local SQLite database for historical traceability. Second, the raw data is sent to the Gemini 1.5 API for semantic analytics. As the dashboard shows, the system generates a plain English summary that is instantly embedded into consolidated PDF and Excel reports. Third, a WebSocket connection pushes live pass-fail counters directly to the operator's monitor. This distribution network converts hours of manual reporting into a 10-second delivery of intelligence. The completed Smart Test QC pipeline provides an end-to-end view of the quality control process. Many in the industry assume that quality automation requires retrofitting heavy programmable logic controllers, or PLCs. While PLCs are for machine control, this edge-deployed stack serves as a non-disruptive data intelligence layer that scales easily across multiple benches. Report preparation time drops from hours to under 10 seconds. This eliminates the need for a full-time employee dedicated solely to report transcription. Operating on a local network with zero human data touches ensures absolute audit readiness. As more batches are processed, the XGBoost pipeline refines its predictions, becoming more accurate over time. By replacing pen and paper with a webcam and a predictive model, factories gain zero-touch quality intelligence that grows sharper with every shift.